Einstein was very unhappy with quantum mechanics, but there have been some myths about what he was unhappy about. The common myth is that Einstein was really unhappy that quantum mechanics had randomness, fundamental stochastic element. Bell came up with this idea of a way to mathematically constrain what long-distance correlations were possible in a local theory. And then he showed that quantum mechanics violates those conditions.
Everything you think you know about Einstein and his objections to quantum mechanics is backwards. We've been told for decades that the great physicist was stubborn, that he couldn't accept the randomness of quantum theory, that he didn't believe God played dice. But Einstein wasn't wrong about quantum mechanics. It turns out he was terrifyingly right. Einstein identified something that should keep you awake at night. Quantum mechanics forces us to abandon one of the three fundamental beliefs about reality. Either quantum mechanics is incomplete, or particles can instantaneously affect each other across the universe, or physical objects don't exist when we're not looking at them. There is no fourth option. Decades later, physicist John Bell proved Einstein correct with mathematical precision. Bell's theorem showed that quantum mechanics definitively violates locality, meaning reality either breaks the speed of light limit or splits into parallel universes every time a quantum measurement occurs. Today's guest, science writer Adam Becker, reveals how our most accurate scientific theory, tested to unprecedented precision, simultaneously remains our least understood model of the universe. We can calculate quantum mechanical quantities perfectly, but we have no idea what's actually happening in the universe when we're not watching it. Adam helps break down all this and more in this special episode of Into the Impossible. Let's go.
Today we're covering a topic that you may think you already know, and that is what is real? What is reality? But I assure you our today's guest has much more to say about that than you would have ever contemplated. And I like to begin, Adam, by asking you, in the context of what we teach our students, we never sit there and talk about what is the interpretation of a pendulum in classical mechanics, Newton's balls, as shown here. We don't talk about interpretations. We don't say in electromagnetism, how do we interpret the magnetic field? Even though it's bizarre, because it involves imaginary numbers. So why do we have to talk about interpretations of quantum mechanics to understand it in any depth?
Yeah, because the math of the theory doesn't line up with reality in an obvious way, right? That's sort of the fundamental difference between quantum mechanics and these other theories that we're talking about, right? In Newtonian physics, the role played in the theory by, a mass is very clear, right? It's a little thing like this, and when you do this, it does this, right? Sure, maybe the electromagnetic field is a bit weirder, right? As you said, it involves imaginary numbers. But, we know what magnets are. We know what things with electric charge are, and the effects that those forces have on those things is relatively clear. In quantum mechanics, that all kind of goes out the window, and it's not actually clear what the relationship between the math of the theory and the things in the world is, except in certain very specific scenarios. And so this leads to questions like, outside of those very specific scenarios, like, when we're looking at the results of an observation, what's going on? Mm-hmm. And that's where we need an interpretation of quantum mechanics to understand what's happening.
There are those that say that we don't need it. No, we just should shut up and calculate. Yeah. How is that philosophy or that school differed in the sense that we teach our undergraduates, effectively we teach them the Copenhagen interpretation.
Yeah.
In advanced quantum mechanics, then we go back to the beginning and talk about the interpretations of quantum mechanics. Yeah. We might even get into many worlds theory. We might talk about that today. But the question that I have is, and yet there are very few situations where we can actually get numbers out of the theory that we can test against experiment. But when we do, those numbers are testable to the highest level of precision of any of the sciences, let alone of the physical sciences. So talk about how useful it is to be able to do calculations, even if you don't understand the interpretations.
Totally. Yeah. Well, look, like I say in the book, What is Real? Quantum mechanics works incredibly well. It's, arguably the greatest success story in all of science. It's an incredible theory. And so as a practical matter, shutting up and calculating is often a pretty good move, right? Because if you have to shut up in order to do those calculations, that's a reasonable price to pay, right? But we don't. And if we ever want to move beyond quantum theory to the next theory, whatever that is, we may need to wrestle with these issues that were sort of left unresolved by the founders of the theory.
We talk about quite often that Einstein was wrong about quantum mechanics. And it's too bad because he could have had a good career. He could have been famous, That and if he had accepted the presidency of Israel. That's all his CV really lacked. Talk about what was he wrong about? Was he wrong about being wrong as he was with the cosmological constant or perhaps dark energy?
Well, so Einstein was very unhappy with quantum mechanics, but there have been some myths about what he was unhappy about, right? So the common myth, and I mean not just in the public, but among physicists, is that Einstein was really unhappy that quantum mechanics had randomness, fundamental stochastic element. And it is true that quantum mechanics has that. And it is also true that Einstein wasn't happy about it. But that's not the thing that he couldn't accept. Einstein had no problem with randomness in theories. He was actually a big advocate of statistical mechanics. What he had trouble with was not even that the randomness was fundamental, which it's not in statistical mechanics, or at least not in the same way. That concern with randomness came out of his real fundamental concerns, which were about realness, about reality in the theory, and about another thing, locality. So the first one was just that the theory seemed, in this Copenhagen interpretation, this shut up and calculate approach championed by, among other people, Niels Bohr, seemed to imply that when observations weren't happening, the things governed by quantum mechanics, the subatomic particles, didn't exist or, couldn't be said to exist. And this was something that Einstein just, said, like, there's no reason to think that that's true. Observation isn't like that. Why should observations matter in this way? And to demonstrate that problem, there was this sort of related problem that he was really the first to identify, which is still with us, which is that quantum mechanics has a tension with the idea of locality, the idea that things, influences cannot travel faster than the speed of light. And Einstein correctly pointed out that the theory as formulated had that problem. And many of his contemporaries, like Bohr, dismissed that and said, no, it doesn't. And then what was discovered later on, after both Bohr and Einstein were dead, was, actually there is an issue with locality in quantum mechanics. It's not a fatal flaw, but there's a tension there. There is something in the theory that does allow for the possibility of some sort of non-local influence or, the appearance of a non-local influence. There's something that requires further work and explanation in the theory regarding locality. And Einstein saw that actually before there was even a fully worked out theory of quantum mechanics. His concerns about locality in quantum theory go back as far as 1909.
In the famous EPR, conjecture paradox, can you explain that? Why is that such a rich source of inspiration for people working on foundations of quantum mechanics and interpretations of it even to this day?
Yeah, so EPR, that showed up in 1935, and the name EPR is the initials of the three people on the paper, Einstein, Podolsky, and Rosen. And the idea there was that you could have a system of quantum particles that shared a quantum mechanical relationship, even though they were very far apart, called entanglement. And Einstein and Podolsky and Rosen came up with this to show that there's this fundamental feature of quantum mechanics, entanglement, that implies that these particles must be sort of connected instantaneously, no matter how far apart they are, if you accept that no fuller description of nature than that given by quantum mechanics is possible. And so Einstein, in his sort of reformulation of this that he did about 15 years later, basically made it clear that the choice in the EPR paradox was between either locality or the completeness of the theory. And Einstein said, he thought clearly the correct answer was completeness. He said, quantum theory works. Of course it works. It's just incomplete. And for a long time, there was no real reason to think that he was wrong about that.
Would that have necessitated what we call hidden variables, or what they have completeness? Could you have locality, completeness, or reality, or did you have to pick like a smorgasbord from one of two of those options at most?
To fill in this completeness gap that Einstein saw, you would need hidden variables or something like that. And so, he was laying this out as a choice of like, either you have to be comfortable with non-locality, which is a pretty high price to pay, or you need to say, well, we're not done yet. There was something missing from the theory that we can find with a deeper theory. And for a long time, that looked fine until this guy came along, John Bell. Yeah.
We'll get to John Bell in a minute. Before we get to John Bell and resolve this issue of completeness and hidden variables, I want to talk about a contender that's come up lately as a springboard to determine what will it mean to have a theory that is complete? What does it mean in practice? And that's called Everettian mechanics, or many world interpretation of quantum mechanics. I like to joke that I've discovered a parallel. Schrodinger's cat is kind of the most famous paradox of superposition, and the Copenhagen interpretation led many people to kind of scratch their heads for a long time. So I've come up with the analog of that for Everettian mechanics, which I want to lay upon you. So that Schrodinger had a cat, but Everett has a rabbit, and it's called Leverettian mechanics.
Oh, no.
Got it. That's a good one. Come on. I'm a dad. I got to make dad jokes. Come on. I got a license. So talk about, why is it, in your opinion, why is it undergoing kind of a resurgence of popularity? Everyone from movies to Sean Carroll and others that really do bolster this interpretation and almost accept it as if it's true. And not only that, they sort of have a belief in it. So first of all, what is Everettian mechanics, many worlds interpretation as it's called? And what, if any, evidence in the physical world would give us credulity in the fact that these things branch at different rates and we could measure? Can we actually ever settle this question of which interpretation is quote unquote correct?
I think we can, but I'm going to come back to how in a minute. But as for why many worlds has sort of seen this surge in popularity, I think there's a few reasons. One of them is sort of steeped in the physics of it all, right? There has been a wider appreciation over the last 20, 30 years among physicists that, hey, actually maybe quantum foundations does matter, because for a long time, it just was not seen as real science and real physics. And the only people really doing it were either like outcast physicists or philosophers of physics who I think correctly recognized that there was a serious problem here. But in the last few decades, what's happened is quantum mechanics has been more established as this theory that really needs to work at all scales, from the small up to the large. And once you accept that, you really can't shy away from the problems that come with it, like the measurement problem. If you want to do quantum cosmology, you need to be comfortable in some way with talking about quantum systems the size of the entire universe. If you do that, you need to be thinking about quantum foundations. There's no way out. Mm-hmm. That, and the fact that things that came out of quantum foundations, directions of research that came out of quantum foundations, like quantum computing, has sort of seen this like full flowering, I think made it impossible to ignore this. And then once you stop ignoring quantum foundations, then you have to start looking at possible solutions. And there are a lot of things about the many worlds interpretation that look pretty appealing to physicists. I don't subscribe to it personally, but I think it's a reasonable option of the options available. Like the things that make it appealing, it doesn't involve modifying any of the equations that we already have, right? It doesn't.
You still have Schrodinger's equation.
Yeah, exactly. You still have Schrodinger's equation. You still like do everything the same way. You just need to make this change in what you think the theory is saying about the nature of our world.
Mm-hmm. And the alternative is collapse of the wave function. And
yeah.
Unitary evolution versus non-unitary evolution collapse. So you avoid that because everything involves unitarily.
Right, exactly. And so that looks pretty good. I mean, the price that you have to pay for that is, oh my God, there are all of these universes, but we don't see them. Where are they? But the theory has an answer for that as well. So, I can understand the appeal. But the other reason it has appeal is not about the physics. And it's just, it sounds pretty good. Right? Wow. It just sounds interesting.
It's a matter of taste.
Well, no. I don't mean it sounds good like as a physicist. I mean it sounds cool if you're not a physicist. Right?
That's why it's in movies.
Yeah, exactly. Right. That's why it's in movies and comic books and
the Spider-Verse. Right.
Yeah.
Mm-hmm. But you mentioned how could we detect it? So I asked this of Sean Carroll. how is it possible that we could even, detect something that where this branchial, function is occurring at the rate of, 10 to the minus 32 of a second, which is, getting close to Planck time. It's only at 10,000 or 10 billion Planck times. Tell me, how could we actually discern the presence of a parallel, alternate, multiverse, universe, Everettian, or otherwise?
Right. So I'm not Sean.
Yeah.
Right? Sean would say, well, you see it in the fact that quantum mechanics is correct, right?
Many of you are watching this on a television, and I know that if you love the cosmos as much as I do, you'll want to subscribe now. It's a little more tricky on TV, but it's well worth your time. Click down below, and don't forget to leave a thumbs up. More minds, more mysteries, more multiverse awaits you.
People say things like, the double slit experiment.
Right, exactly.
I've never really fully bought that, but maybe can you make the case?
Sure. Yeah. If I put on my Sean Carroll hat and pretend to be Sean Carroll for a second and really be Everettian, I just saw him a week or two ago, then I'd say, yeah, well, look, the fact that we get an interference pattern in the double slit experiment is something that you can't coherently explain without many worlds or something like that, or you have to, choose one of these other less palatable options. And so out of the available options for explaining how quantum mechanics works, this is the best one, right? And I don't know that that's exactly what Sean would say, but that's the kind of thing that you get from Everettians. And I understand why they say that. And again, I think this is reasonable. I'm just not convinced that they're correct. I don't think that we currently have a way to detect this or figure out which interpretation is correct. But I think that someday we will, because what's going to happen is one of the few things that I think everybody agrees on within physics about quantum mechanics and quantum physics is that it's not the final theory, right? We know we're not done. At the very least, we need a theory of quantum gravity. And that means we need to move beyond this theory at some point. And historically, it is when we move beyond a certain theory that we get a new light onto what that theory was saying in the first place, right? When we moved past Newtonian physics, we learned new things about what Newtonian physics had been saying all along. We had a new way of looking at it. And the interpretation of quantum mechanics that we choose may end up influencing, in what direction we make a discovery that lets us move past it to the next theory. And so it may be that the next theory comes with a way of looking at the world that's really best compatible with one or a certain way of interpreting quantum physics, and may even come with a way of experimentally distinguishing between different interpretations of quantum mechanics.
Is there any other example of a theory that works, but nobody understands how it works?
Yeah, that's a great question. Honestly, there are theories that people commonly misunderstand, but it is hard to think of a theory that people take as seriously as quantum physics that is as poorly understood at the fundamental level as quantum physics is. And I think that's really striking, and one of the reasons it's a problem.
And let's talk about John Bell. How does John Bell kind of come to either the rescue or perhaps final humiliation of EPR, of Einstein and his colleagues?
Yeah.
What was his role? And first explain, if you would, what are hidden variables and why did this pose such a contentious problem for many decades?
Absolutely. So hidden variables, the idea there is realizing in a way Einstein's dream, right? Saying, yeah, you know what? Quantum mechanics works really well, but it's incomplete. And there is some hidden thing that takes this fundamentally probabilistic theory and actually makes it deterministic, something that actually determines these outcomes that we are seeing that we can only ascribe probabilities to. And again, the probabilistic stuff isn't what Einstein was really concerned with fundamentally, but finding a way to solve that problem would, get rid of the problems, or seemed like it would get rid of the problems that Einstein had. And this brings us to Bell, right? Because Bell, it's very interesting. Some people have said, yes, Bell's the man who proved Einstein wrong. And other people have said, no, Bell's the man who proved Einstein right. And I understand why they both said that. I'm more inclined to say that he proved Einstein right, in that Einstein was concerned about locality in quantum physics, and Bell showed that he was right to be concerned about that because it's a problem. What Bell did was he looked at the only hidden variable theory that existed at the time that he came up with, that he was thinking about this. Bell was thinking about this originally in the early 1950s, and then he put it down for a little while, came back to it in the mid 1960s. And he was looking at the only hidden variable theory that existed at the time was a thing called Bohmian mechanics, which does, assign this sort of deterministic hidden variable picture to what's going on like under the hood of quantum physics, but at the price of introducing non-locality. And so Bell looked at that and said, does it have to do that? Is that a general feature of quantum mechanics, or is there a way around it? And so what Bell did, and I want to emphasize, he did this without quantum mechanics. He just did this starting from the assumption of locality, and not from the assumption of hidden variables or anything else like that, just locality. Bell came up with this idea of a way to, mathematically constrain what long-distance correlations were possible in a local theory. And then he showed that quantum mechanics violates those conditions. So, Einstein with EPR, he had shown that with quantum mechanics, there was a choice between its locality and its completeness. And what Bell showed was it's worse than that. Either nature is non-local or quantum mechanics is incorrect in certain situations. Or there's some weird third way out that involves something like many worlds or something else. There are ways to wriggle out of Bell's, theorem, but it's a very narrow door.
I viewed this as sort of a very instructive, the sociology of science. Even the great Einstein was sort of shunned. And certainly you make the case in the book that Bohm was really kind of, traumatized by his outcast. What is the role of consensus in science? I mean, going beyond the headlines and 97% of scientists agree, whatever that means. Is there a place for consensus? And what was the damage done?
Yeah.
And what opportunities came out of that for people like Zeilinger, Clauser, and others that we'll get into in a minute, from the shunning of people like this tragic figure that Bohm really and ultimately is portrayed as in the book.
Yeah. No, David Bohm, he was shunned by his fellow physicists for, saying the things that he said about quantum physics. And then he got, run out of the country for being a communist and couldn't find work. Even though he had recommendation letters from Einstein and Oppenheimer, just about the best recommendation letters you could ask for, he ended up going to Brazil. And then even though he ultimately decided that communism was wrong and that he was no longer a communist, he didn't feel comfortable coming back to the US after the experience that he'd had. And I think understandably so. But yeah, I think that there is a place for consensus in science, right? And I think even David Bohm would agree with that. For example, Bohm was part of a scientific consensus that quantum mechanics is correct. Right? Mm-hmm. And Naomi Oreskes, author of Merchants of Doubt, she talks about consensus as sort of one of the products that science produces, is scientific consensus. And it is absolutely true that there's a scientific consensus that quantum mechanics works. It is also true that sometimes scientific consensus is wrong, but usually when science is functioning properly, that, the cases where scientific consensus is wrong are usually more like questions around quantum interpretation than they are around questions around, does quantum mechanics work at all? The key point there is that, it goes back to the question you were asking about, can we know if there are these other universes? One of the reasons quantum foundations is hard is because quantum foundations, with rare exceptions like Bell's theorem, doesn't make contact with empirical, experimental science. Right. And so it was only when Bell found a way to have quantum foundations make that contact that a new opportunity for consensus arose. And I think that part of what we're seeing now with the increased interest in quantum foundations is essentially a delayed reaction to that, to say, oh, yeah, I guess actually this does matter. I think there is an important role for consensus in science. When science is functioning properly, we need scientific consensus. We just need to be careful about it.
Since you wrote the book, at least two scientists have won the Nobel Prize for quantum foundations, Anton Zeilinger and John Clauser. Talk about, and that was obviously due to your book. You put them on the map, Adam, let's be honest here. Talk about the experimental approach to interpretations of quantum mechanics, the work by Clauser, by Zeilinger, and their colleagues. Yeah. How does that fold in, and why does that still matter today? Haven't we proven, shut the door completely on this, Sophie's choice between completeness and locality and reality?
Yeah. So Bell showed that there was this choice, right, between the accuracy of quantum mechanics, its correctness and locality. And so that meant that you had to test quantum mechanics in these specific scenarios that, as it turned out, no one had tested it in. Some people had come close, but no one had actually done the test. And so what Clauser and then later Aspect and Zeilinger did was they actually performed that test. So John Clauser led the charge to do the first experimental test, and he did this up at Berkeley in 1972 with Stuart Friedman to actually do the first experimental test of Bell's theorem, to test quantum mechanics in these conditions. And Bell thought that quantum mechanics would, come out on top. He thought that it would work. Clauser wasn't so sure. Clauser was hoping that it wouldn't, which is, understandable, right? In his first letter to Clauser, Bell said, you got to think that quantum mechanics is going to work, but there is the small chance that it won't. And in that case, that would shake the world, right? Clauser wanted to shake the world. Yeah. And I think it's a testament to his skill as an experimenter, both that he was able to do the experiment and that even though he was hoping it would turn out one way, it turned out the other way. And he published that result. And then when another team, I think over at Harvard, did a similar experiment and found that, no, actually quantum mechanics was wrong, Clauser went back and did his experiment again at a higher precision and in, a way I think more closely resembling the Harvard team, and found, no, his initial result was correct, even though it's not what he wanted.
Which is a good thing. I mean, that's a good sign of a scientist that's not dominated by confirmation.
Exactly. Yeah. It's how science is theoretically supposed to work.
Right.
Aspect came in and saw this debate going on between Clauser and the others and said, by the time I get an experiment up and running, it's going to be too late. That'll be resolved. But maybe I can find a different twist. Maybe I can get the experiment done. There's a thing that has to be done in these experiments where you switch detector settings at different ends of the experiment. And he said, maybe I can find a way to make that happen really, really fast, which would close certain loopholes around, slower than light connections between the two ends of the experiment. And he did find a way to do that and publish that result. And he also, Clauser had a lot of trouble finding a job. Aspect went and talked to Bell before he engaged in this. And Bell said, do you have a permanent position? Because otherwise you shouldn't do this. And Aspect did. And after he did it, he went and gave a lot of talks about it and was very sort of persuasive that this is interesting science. And that had a really big effect just on the culture of the field. And then Zeilinger came in and closed another one of these loopholes around detector efficiency at both ends of these Bell experiments. And, this third generation of Bell experiments is sort of, led us into this modern era of quantum information science. They're all really spectacular and I think beautiful experiments.
So 2 final questions. One, can you explain quantum computation? Why does it have so much promise? Is it hype? Do we really expect to learn more about the physical universe than just learning about how to solve a Hamiltonian or a protein? Quantum computers are very good at describing how quantum computers work. As Feynman pointed out in the 50s and 60s, what else can they do? Can they really do anything superior? And can we connect them to your new book? Are they also going to be part of an AI dystopian future?
I mean, quantum computers, it's not just hype. If we can get quantum computing to work, we can use it to, as Feynman and many others said, it's not just him, we could use it to learn a lot about, material science, quantum mechanics. There are certain algorithms that we have not been able to find classical computing algorithms for, but quantum computing algorithms that can go really fast for like factoring numbers. It's really, it could be very interesting. We don't know for sure that we're going to be able to get it to work at the scale that we'd need it to for it to actually be practical. And even if and by we, I just mean humanity here. And even if it turns out there is a way to do that, that doesn't mean that it's going to replace the kinds of computers that we have now. I don't think it's ever going to do that, both because quantum computers are not better than existing computers at many other tasks. They're just as good or worse. And also, it seems unlikely that we'd be able to get quantum computers to work that would not be sort of very delicate, because the level of control is literally quantum needed to make them work. So it's not hype, but it's also, still technology that we're figuring out. We're trying to see if we can prove it. The answer to the question, is it going to be part of this, AI future? It really depends on the question of, well, how well does it work out? Silicon Valley would like it to work out very well and, perform all kinds of magic tricks for us. Silicon Valley wants a lot of things.
Okay, so Adam, what is real?
Okay, so my favorite Amazon review of either of my books, or maybe it's Goodreads. Yeah, I think it is. It's a Goodreads review of What is Real, and it's art. Like, I should print it out and frame it. I love it so much. It just says, what is real? The author's answer, I don't know. And it's like, buddy, there's a question mark there at the end of the title. And the subtitle has the word unfinished right there in it. Like, if somebody could explain to you in just 300 pages what the answer to the question, what is real, would you believe them? Like, I don't know. But I do know that whatever it is something that makes quantum mechanics true. Right? Or at least approximately true, right? Because like quantum physics, quantum mechanics, quantum field theory, these are the most accurate theories that we've ever devised, especially quantum field theory. There's got to be something in the world that those theories are about that makes them approximately true.
We hear a lot about all sorts of misapplications of quantum theory, as well as things like quantum healing, quantum spirituality, even things that are supposed to entangle us and how those relate to souls and the afterlife and so forth. What would Einstein make of this? Would he call it nonsense? What do you make of it?
I can't speak for Einstein, but I don't. I do think he would have thought it was nonsense. I can't, imitate his voice well enough to say what he would say, but he certainly would not have thought that any of that was good. I think he would have just rolled his eyes and said, yeah, that's what humans do, right? I think it's nonsense. There's certainly no connection to quantum mechanics with any of that stuff. And I also think that these sort of misunderstandings around what quantum mechanics means and the sort of hole in our understanding of it that's left by not investigating quantum mechanics or the quantum foundations rather, for a very long time, left an opening for that stuff, made it easier to sort of sell that kind of snake oil, to say that, quantum mechanics proves that there's this fundamental role for the observer and stuff like that. But I will also say, that is also just stuff that humans do. Humans are always going to find ways to misapply, truths and try to do this kind of thing. And, if you're feeling pessimistic, you can say we're always going to con each other. If you're feeling optimistic, you can say we're always going to look for hope even where, we shouldn't. But either way, this sort of misinformation and disinformation is out there, and you got to be careful.
Adam Becker, thank you so much for your time on both of these wonderful books. We'll have links to everything down below.
Thank you so much.
And so much more.
The implications of quantum mechanics stretch far beyond the laboratory. And if you enjoyed exploring how our most successful theory might be fundamentally incomplete, you should definitely check out my episode with cosmologist Sean Carroll, where we dive deep into the many worlds interpretation and whether every quantum measurement literally splits reality into two parallel universes. Click here and don't forget to subscribe.